Hello and welcome back to Calculus 1 section 3.6 on derivatives as rate of change. We already said that derivatives measure change because it's the slope, right? And slope shows the progression in time. So the slope can be going up, right? In which case it shows positive change. It can go down to show the negative change, or it could be flat and there's no change, which means derivative is zero. So we learned that long time ago. Now what we are going to do is we are going to define some mathematics for application. For instance, we'll talk about position, velocity, and acceleration, and so on. So let's take a look at that stuff. So first, we're going to take a trip from point A to point B, which is, let's say, 10 miles. And from point A to point B, you went 10 miles in 10 minutes. So if you have this calculation, right, you can compute what we call the average velocity, because the average velocity is simply calculated when you divide the distance you covered by the time it took you to cover that distance. So velocity average is going to be simply 10 minus 0 divided by 10 minus 0. Now this is in miles and this is in minutes. So you are getting that you covered 1 mile per minute. Now we do not measure things in miles per minute. So we use the conversion where 1 hour has 60 minutes, and then minutes and minutes will cancel. Now, so if you write out the units, you always know which way to put the conversion factor, because you always want to cancel the one you don't want. So this is why we put the minutes on top and hours on the bottom, because the minutes were on the bottom and it will cancel. So now all I get is 60 miles per hour, right? So 60 miles per hour, and you are used to, the MPH thing, but 60 miles per hour. So the average velocity, the average speed was 60 miles per hour. Now in physics and Calculus 3 and differential equations, you are going to distinguish between speed and velocity, because velocity is a vector which has the direction and magnitude, meaning direction which way you go, and magnitude how fast you're going, which is called speed. So speed is technically part of velocity. But for our one-dimensional motion here in this room, we can say they're one and the same, because we do not care about direction in our case, because you always go from A to B. That's one-directional motion, so we don't care about distinguishing between velocity and speed. However, as soon as you move from one-dimensional mathematics here to either physics or Calc 3, you have to distinguish between velocity and speed, because they're not the same thing. Speed is a part of velocity. Anyway, so what does the average means? Well, that means that in some cases you were driving faster than 60, and in some cases you were driving slower than 60, and they all average out and smooth out into driving on average 60. See, if you say, oh, my speed was always 60, I would say no, because in that case it would mean that the car was already moving 60 miles per hour in front of your house, and you somehow managed to time your jump into the car correctly. And then over here, getting to, let's say, campus, right, you jumped out of the car while car is still moving at 60, right, and you ignored all of the stop signs and red lights and everything else along the way, right? So average is the average speed, just simply knowing that you went more than that, went less than that, right? Eventually you came to the parking lot and you parked the car and the velocity was 0. Well, that split second was still averaged with everything else to give you 60 miles per hour. So clearly the average speed doesn't tell us the whole story, right? You can calculate the average speed, but you can calculate the average speed only when you are done with your entire trip, because you have to calculate the total distance traveled divided by the total time it took you, and that's going to be the velocity average, or the average speed. So now velocity average is going to be your slope of the secant line, which was, the basic algebra, where you are going to take d2 minus d1 divided by t2 minus t1. Has nothing to do with calculus. It's a basic average that we learned and reviewed and all of that good stuff. What about calculus? Well, calculus considers the notion of what we call instantaneous velocity. That is the speed of an instant. And how short is the instant? Very short, right? It is that split second you look at your speed when you see, right, a squad car following you. Just seconds before you feel safe and secure and protected, right? You still look up at your speed, right? So the speedometer in your car constantly evolves as you push either of the two pedals. If you push the gas pedal, it's going to show more. If you push the brake, it shows less. By the way, if you have a car with 3 pedals, it's time to upgrade. It's 21st century. No, they're not.
Yes, they are.
They're annoying to everyone else because they roll back when you are on a hill. Anyway, so and they're less efficient and everything else. Anyway, so you have this notion now that the speedometer is showing the instantaneous velocity, which is clearly different than the average velocity. So velocity of an instant, you can take a picture of it, right? It's let's say at 48 miles per hour. You can take a picture of it, right? To take that picture takes a fraction of a second, right? And that was your speed at that instant, which is why it's called instantaneous. And very quickly you will connect that average is like a movie, right? You take a look at the whole trip, right? And it's like a time lapse, right? And you have the instantaneous, which is just a split second in time. So we want to focus on instantaneous because that is what you compute with the derivative. So instantaneous velocity is the velocity that you get when you take the derivative of the position function. So, right? And position function is generally labeled as S of t. So instantaneous velocity is given by the derivative of the position function S of t. You can compute in time. So let's go. S of t, position function, v of t, which is the derivative of s in time, is the velocity function, which will give you every velocity of an instant. Just give me at what time you want to know. And finally, acceleration, which is derivative of velocity, just for the hell of it, it's not in the book, jerk, the derivative of acceleration. you can experience all of these. Let's first talk about the notion of a change. See, your car is parked, not moving, velocity 0. And because it's not moving, it is not covering any distance. If you do not get car to move, you are not going to school. It's very simple. Or wherever you're going. So you press accelerator, which means you give it some acceleration. Acceleration changes velocity, and now you have velocity. You're moving. And what is velocity doing? Velocity is changing position, changing the distance, so you cover the distance, right? So think about it. You do not get to move. You do not get to go anywhere until you accelerate from the 0 state. You have velocity of 0, and you have to change that velocity from 0 to anything positive in order for that velocity to change your position. And then you get to get somewhere, right? Jerk is change in acceleration. So you experience jerk when you press any of your pedals in a 2-pedal car too abruptly, right? If you press deceleration, which is brakes, that's just negative A. If you push decelerator, which is brakes, your face is trying to hit the steering wheel. If you are sitting in a car that has good acceleration, a lot of horsepower, a lot of torque, right? Like Tesla car can, with ludicrous mode, like does 0 to 60 in 2.3 seconds. Try to see the YouTube video of people experiencing that, those G-forces, and the amount of cursing that it's involved every time someone tries a Tesla acceleration. It buries you into the seat, right? Because that's what the jerk is, right? So jerk is a rapid change of acceleration. You can press your gas pedal, which is acceleration. You can press it slowly, right? In which case you will pick up velocity slowly and you will not experience jerk, right? Or you can floor it and then get, right, jerked into the seat. And then it will, right, acceleration changes velocity, velocity changes position, right? You are off to the races in that case, right? So you can see that the derivative progresses. And then when you asked me, do we have higher order derivatives? Yes, because with your position function, you take the first derivative to get into velocity, second derivative to get into acceleration, third derivative to get into jerk. There is more. Take physics, okay? And then enjoy physics. So now, we are interested in understanding the motion, right, of the objects around us. Last lecture, unfortunately, didn't end up on a stream because the network died. We talked about the pendulum, right? And we took the derivatives. Well, now that it was not featured, let's just quickly switch to it and take a look one more time at that calculation, because now it's relevant again. You have a distance function, the position function with that d. Could have called it s of t, because position, right, is labeled s of t. The word position has an s, so clearly, right? And you have the time, right, because the motion will happen in time. And you see me taking the derivative to get velocity, and we could have taken another derivative of velocity to come up with the acceleration of the system, right? And all of those describe where, like the d, where the object is. V describes how fast it's going for a given time, and acceleration, obviously, what is the acceleration at the given time. So if I have a specific case, I just plug in the numbers and I compute, and we are all done. Now, we are not going to work on this example. We are going to take a look at, first, we're going to take a look at what we call projectile motion, which is downward opening parabola. And I am going to do a quick experiment here in class. Are you ready? Everyone ready? We need to see the parabola. Ready? There we go. So, what you witnessed is this. So now, I am going to say that S of t is equal to -1/2 gt squared plus v0t plus y0. This is the function that calculates the position of the object that is under this kind of motion. Anything you throw, apart from leaves and paper, stuff like that. So anything that will, fly without air being significant to change its trajectory, anything you throw will go with this equation. So now you have few things that are part of this equation. Clearly t is time, because this happens in time. It might take 1 second, might take 10 minutes to get somewhere, right? And then you have the g, which is the gravity. You can toss things on Earth, but you can toss them on the moon, and you can toss them on a Mars. Much larger issue than the poisonous air in Mars is the gravity, because Mars is not as big as Earth, has smaller gravitational constant, obviously, so you are going to feel like a superhuman going to Mars because you can jump further and jump higher and so on. But give 10 or 15 generations of people born on Mars, right, in the evolution, when they come back to Earth, you can just flick and kill them, because they were not going to be so dense and so strong, because they were born after 15 generations on the planet that had smaller gravitational pull. Same would happen with moon and whatever else is smaller, right? So gravity plays the role, right? Then you have the v0. That's your initial velocity, right? Did I just do a little toss, or I really scaled it, right? That's going to be the v0, and then y0, the height from which you are tossing, which is why you want your basketball players to be as tall as possible, because it's much easier to make the hoop if you're shooting from 7 feet height than if you're shooting for 3.5 feet height, right? Because the hoop is on the standard height. So volleyball players and others as well. So you have all of these features in the formula. They all make sense, and also dimensionally they make sense, because all of this is done either in meters or feet, depending on which system of units you want to observe. Now, for some common sense knowledge, and it's always embarrassing if you don't know these things, gravitational pull 9.81 meters per second squared if you are talking metric, or gravitational pull of 32.2 feet per second squared if you are talking in imperial units, the ones that we use here. Very costly mistakes when you design the rover in meters and you program it in feet, and then you just and just ram it into the planet. Anyway, so now we have these constants, and we are ready to talk about the velocity, right? Velocity in respect to time, which is going to be the derivative of position function. So now we know how to take the derivative, right? Derivative is taken in respect to t, which is why the t is in the denominator of the derivative there. We copy the constant, which is -1/2 g. G is a constant. You see that in red. So you copy the constant g. And now the derivative of t squared is 2t. Beautiful. And then plus constant v0, right? Because that is just how fast did you throw something. And then what's the derivative of t? The derivative of t is 1. Good. Plus 0, which is the derivative of y0. That's just a number. It's just a constant. So now you have your velocity formula, v of t, and that one is negative gt plus v0. Those of you who took physics have seen this formula most likely in the form of velocity final is equal to velocity initial plus acceleration times time. Ah, yeah, right? So now put your acceleration to be gravity, negative g, and you have the same, right? We said the v0 is initial velocity, which is the toss. So these formulas, right, are all the same, and they are derived through math, just used in physics. Yes?
I remember, there was a significance in which g used 1. Does that still matter?
Well, if your problem is in metric, then you use the first one. If the problem is right, so it depends on the units, right? You will read the problem. If they mention feet, you are using 32.2. If they mention meters, then you're using 9.81. And I believe your book does both. So they are going to slap you for that in my math lab. I have no doubt. So great. So guys, you learned one of these formulas you recognize one of these formulas from physics, and now it's time to take another derivative of the velocity, again in time, to calculate acceleration. And that's just going to work out to be negative g, because the derivative of t is 1 and the derivative of constant v0 is just 0. So we found that acceleration is, but we already knew that, right? Acceleration due to gravity. When you drop something, right, it accelerates with 9.81 meter per second as it goes down. Now, it's always tricky to do this, but I'll give it a shot. Now you really have to look to see which one is going to hit the floor faster, right? Ready? One more time. You see? This one always hits the floor faster. Why?
Because part of the force.
Exactly. So I release the marker on your right. I release the right marker as soon as this marker hits the same height, but I gave the initial velocity, which is the difference between and being angry, right? So when you drop something, the only acceleration, right, the only velocity you get is due to acceleration. If you slam something into the ground, you still have the acceleration due to gravity, but you have an additional velocity of the anger, right? So that's the difference between dropping something on accident and slamming it. Bundle of physics formulas that you can use to compute the position, velocity, and acceleration of an object that is in, let's say, parabolic motion, right? If you fire something out of a cannon, whether it's a chicken or a person or the round, right? Cannonball, yes. Hi.
What's that ancient T formula in physics? What's that used?
we're going to talk about, you're probably talking about height, right? Not 300, 400. 400 years ago, like, this would be your last sentence. But now, and we are so...
Depends on where you are.
No, I'm just kidding. Come on, you know. Anyway, so S of... I can't even write it. Look what I did with the S now.
That's because you only get 4.5 hours of sleep.
That's plenty. S of t is going to be negative 1/2 gt squared plus v0t plus y0. V of 0, oh sorry, V of t. Now I can't write anything anymore. V of t is going to be negative gt plus v0. Perfect. And acceleration is going to be negative g. So we have this one, and now there's the question of, can we calculate the maximum height of the object when something goes flying across the room because we threw it, right? And that's where the maximum height, h. See? That question was right on money. All right, so what happens when something goes up, when you throw something up, whether you throw it forward or you throw it straight up and catch it, what happens to the object? What happens?
Accelerates until it is force and then it drops.
Yeah, but what happens at the highest point?
Zero.
It stops. That's the one that I need. So for the max height, object stops. At the max height. And that is very important, the fact that the object stops. So that means that I can use the formula velocity in time is equal to negative gt plus v0, and I can set v of t to be 0. Because the object stopped, right? The object stopped. And because the object stopped, I can say it has a 0 velocity. And when you set velocity equal to 0, now we calculate the time t at which we have max height. I missed an age over here. There we go. Max height. Good. So now we calculate the time at which we have the max height. And to find the height, use S of t with the time. Let's do the example of this, which is why I had to get the book. So, since this is not a physics course, you are given the formula, obviously, and then you have to calculate the rest. Oh, perfect. A stone is thrown vertically on Mars. So, Mars, not the bar, the planet. So you throw a stone vertically on Mars, and the g on Mars is 12 meters per second squared. It gives you the formula S of t as negative 6t squared plus 64t plus 192. And we want to find the functions, and then we want to find the max height. So we calculate the velocity by taking the derivative, which is negative 12t plus 64. We already know that acceleration is going to be negative 12 because when you take a derivative, right, it works out for the gravity of negative 12. So now to find the max height, we said you set velocity equal to 0. And as you can see, the only unknown quantity there is t, which would calculate the time at which max height occurs. So t is going to be 64 divided by 12. Now, what's 64 divided by 12? It's 5.3 seconds. So you throw something upward on Mars and you have to wait 5.3 seconds to reach the max height. So max height happens in time at 5.3 seconds. So now we are going to calculate, so for max, well, let's just call it age max. So height max is going to be S calculated at 5.3, which is negative 6 times 5.3 squared plus 64 times 5.3 plus 192. Now you take the abacus, you punch all of these numbers in, and you're done. So negative 6 times 5.3 squared plus 64 times 5.3 plus 192. Told you have superpowers there. It's equal to 362.7 meters. My height is 2 meters. So, yeah. Cool. Oh, wait. This was in feet, not in meters per second. Well, not impressive anymore. I'm not thinking at all.
That's what I say.
Yeah, because yes, 9 and 12. Yes, you're right. It's 360 feet.
That's still pretty impressive.
Yeah, but you're on Mars. It's about, it's not exact, it's about 2.5 times weaker gravitational pull. So think of whatever you can throw here, it should be at least 2.5 times more. Can you toss something 100 feet? So, yep, that's it. All right, one more example, and this one is going to be really cool because we are going to switch our gear from physics to business and economics, and we are going to take a look at the cost analysis using, again, derivatives and averages to see if our production is set up properly. You all heard 99% of businesses fail. Well, of course, they can't do the cost analysis. In order for business to survive, it must be profitable. If anyone ever is trying to convince you that profit is a bad thing, you can plainly tell them just in the face they're a moron, right? Because in order for a company or a business to stay competitive, it has to invest in the product development. And that costs money because engineers and development and everything costs money. It's a cost, right? If you have an engineer working there for 100K, right? Well, that salary has to come out of somewhere. And you have team of people. So you can go from version 1 of the phone to version 2 to version 3 to version 4 and 5 and version 11. Eventually competing against other companies that do the same thing. Otherwise, we would just have a version 1 on the phone with any development, further development, and we would still be driving the same cars and the same everything. So in order to fuel the progress and development in tech, the company must be profitable, otherwise it has to go under. Now the profit is the revenue minus the cost. Revenue is what you collect from sales of your product. So if it costs you $3 to make something, you better be selling it for $6 so that there are another $3 in there as a profit. 6 minus 3, right? And there is a $3, and that $3 goes on the pile. And then using those monies, you can hire engineers and research or buy other companies, right, that have the technology that you want, and use that money to further your product and then offer better product to your customers than what you had the year before and the year before and so on. So you see that development on, because every year there's a new model for a car, every year there's a new cell phone model, every 6 months there's a new computer, right? So the research and development is extremely important, and it's fueled from profits, right? So now, in order to keep the profits up, you have to keep the cost down. That means that the more you produce, it should cost less. Otherwise, you are going to get into the problem of too much cost and obviously not much profit. So now, in order for us to understand, so this is going to be cost analysis. We are going to talk about the average cost, which is C with the bar on top, which is your cost function divided by the units. I'll just say X equals units produced. And then we also talk about marginal cost, which is just the derivative. Oops. Sorry. Didn't see that. Just the derivative. So in the business world, they do not use the word derivative, they use the word marginal. Now, what are the differences between these? Well, we already know what the average is. What we are going to see now is that the more you produce, the cost of the production goes down. And that should be common sense, because cost has variable cost and a fixed cost inside. Fixed cost is the cost of the machine. So let's say that this marker that I have in my hand right now is the only marker ever produced. Ever. So this Expo company opened their facility, the factory, hired all the workers, hired all the engineers, hired everyone, and they just produced this one marker and then shut down. All right? That's it. What is the cost of this one marker? Cost of everything, right? Now, what was cost of everything? Factory. which is buildings and rooms and bathrooms and everything that it has, right? Including all of the machines, including the security person outside, everything, right? That's very costly, right? If the machine that makes this is, let's say, $1 million, then the cost of this single marker produced is $1 million to make up it, you know. But where are all the design people? Where is the artist who designed this? Right? All of that stuff is there, including the people that run the salaries for everyone who worked and everything else, right? It's a lot of cost right there. Now, if that company produced 2 markers, that's it, these 2, and shut down, what's the cost of each one? Well, now it's $500,000, right? So if the cost of the setting up the production and design and everything was $1 million, if you produce 1 marker, then that marker costs $1 million. If you produce 2 markers, then each of these is $500,000 each, right? Well, what they produce is 1,000 an hour, so, right, you can have them for 50 cents, okay? It's okay. So you see the same thing with dealing with the Tesla cars, right? The first model, Model S, was out at 85, 90K, up to 100K, right? And obviously, at that price range, only few people are able to. Now, some people that immediately realized of how insanely better that car is than anything else actually took the second mortgage and bought a car, right, all the way in 2013, and you can find those documentaries. But for the vast majority of the people, would not even consider buying it at 85K because it seems it's too expensive. But now that there's the economy version on the market, and supply the market. So clearly, setting up the production for these things is not easy, especially when you have a very unique product that you can't modify other machinery for, right? It's very easy for a company that has an established line of cars to modify their machinery from 2017 to 2018 model, and then 2018 to 2019, and just change a little bit in the production, and you're good to go with a new model. But to set up something completely new costs a lot of money, and that's that fixed cost. So the first models are going to cost a lot. What's the next model? First one was S. What's the second one? X. Right? And that one is 140K. And then economy model, now they're going to have Y and all the other things, right? So now, what we need to see in the problem I'm going to do now is that the more you produce, the cost of the production goes down. If that mathematics checks out, you have a viable business that is going to survive. If the cost goes up, the cost stays flat, your business is doomed automatically. Now, if you want to know more about that, you're going to go take courses in business and economics, and you're going to learn the details of that stuff, right? We're just going to run some numbers here for the sake of the example. And I really like the example they give here because it works very nice with calculation and explaining all these things. So we're going to take a look at the cost function for the first 1,000 units produced, given as negative 0.02 x squared plus 50x plus 100 for the first 1,000 units produced. If you ever wondered what mathematicians are good for, they come up with these functions, given the set of constraints and things like that. So they do these analysis, and you can get contracted by the companies to do these kind of things, and you charge a lot of money for that. All right, so let's take a look at our average cost function. So average cost is going to be the cost function divided by the number of units produced. So that's going to be negative 0.02x plus 50 plus 100 over x. And we are going to also find the derivative, which is the derivative of the cost function, and that one is going to be negative 0.04x plus 50. So these are our two functions, and now we are going to analyze the cost for the first 100 units in the production. So I'm going to calculate the average cost per unit produced, and that is going to be negative 0.02 times 100 plus 50 plus 100 divided by 100. So you plug in 100 into the average formula, and you get negative 2 plus 50 plus 1, which gives you, put a dollar sign there because it's money, so it's going to be $49 per unit. So it costs for production of first 100 items. I don't care you're talking about markers or cars or flip-flops, whatever. To produce the first 100 units, it's going to be on average $49 per unit. And then you want to calculate the derivative at 100. This is calculating the cost of the 100th unit. See, a single unit. You see, when you have a production line, these guys are going to come out on a conveyor belt, right? And then they're going to go into packing. So this is unit number 98, unit number 99, unit number 100. So the derivative of 100 is calculating the cost of making one, just this one, in particular 100th unit. So you ignore 98, you ignore 99, and you pick up the unit number 100, and now this calculation will tell me how much it costs to make this one unit. So now, that's negative 100 plus 50. Hey, this. Let's see if I can restore it. You will get 46, and that would be the cost of making that. And you see that it's a 49, and now it's a 46 to create this one.
So it is a viable business.
For the first, yes.
The first 1,000 units.
Well, we're going to do now for 900 as well. It's going to work out. But so negative 0.04 times 100 plus 50, and you are getting $46 to make the 100th unit. So now you see that on average, the cost is 49 per unit, but when you calculated the 100th unit, actually it's a 46, which is less than 49, which means that the cost is dwindling down, right? Because this one has 100 different units inside, and on average they cost 49. Now you have, and you calculated a single unit on 46, right? And that's. Now we're going to do the same calculation for 900 units produced, and we're going to have our average cost for 900, which is negative 0.02 times 100 plus 50 plus 100 divided by 900. And that's going to be negative 2 plus 50 plus, and when you cancel these zeros, 1 divided by 9 is 0.11 and so on. So oh, hold on. No, this is 900. So that's negative 18. Holy nightmare. I saw something is wrong because the numbers were not. It's negative 18 because it's 2 times 9, right? So that's 18. So that's going to be 32 and 11 cents per unit. And we immediately see, oh my God, come on. There we go. And now we immediately see that the average cost is down. We are going to compute C prime at 900, which is negative 0.04 times 900 plus 50. That gives us negative 36 plus 50 equals to $14 to make the 900th unit. We see that this business model, right, the cost analysis is really good, right? Because the more you produce, the cost to produce is less, which is why, right, you can give a discount for the bulk. If you're going to buy 1,000 units off of me, right, I don't have to charge, $100 per unit like on the top. You see that 49 average there? You want to charge $100 because you need a profit. You can't sell at cost. You sell at cost, there's no profit. And if there's no profit, there is no new, better, upgraded model. And if there is no new, better, upgraded model, your competition eats you alive. So if you are going to buy 1,000 units over here, well, it's going to be, 100 units. 100 units is going to be at 100 a unit. If you're going to buy 1,000 units, I can drop it down to 60 per unit. Right? 60 per unit. Because look at that. So those prices that you see for the bulk and stuff, they're not arbitrary, guys. The companies that are there in business, they're doing good business and they're selling their product. These things are computed and they're profitable, and because they're profitable, they can stay current and relevant on the market and continue. Those who can't, they're out. Yes?
Well, we can
Graph for what? Well, as you can see, these are that's a polynomial function, so it's,
Okay, I think maybe it makes something bad.
because this is downward opening parabola.
Yeah.
So as you can see, as x goes further out, it's going to curve down. So it shows that the cost is less and less the more units you produce on the long run. It's a downward opening parabola.
Yeah, I was just gonna something in macros.
Oh yeah.
It was like it's like horizontal and then it comes down because you're able to produce more.
That's a production graph. This is a cost analysis. So this one will be a flip, because you want a cost to go down and you want the revenue and production and profit to go up. So when you're looking to a function that is going up, hopefully it's a profit, right? Not a cost. You want a cost to go down, right? So that's one of these things. All right.